count us in.
You're on, eventually.
Okay. Good afternoon, everybody. Dr. Daniel Barth here with the How Do You Know program, and today's guest is my good friend, Kent Martz.
I had nothing else to do, so here I am.
We're
Not true, but I still am here.
We're happy to be back here with you, episode number
fun.
69.
I'm looking forward to this episode.
Yes. This is exciting and good stuff. So, the first thing we want to get to today is an update on the Eratosthenes project. I'm working with Professor David Sederberg from Purdue, who's a physics professor there, and he and I are collaborating on this Eratosthenes project, or International Measure the Earth Day. We're hoping that our entire How Do You Know audience is going to be participating with us, and we'd like to detail what we're going to be doing. Eratosthenes, you may know him. He's an ancient Greek scientist and mathematician, and almost 2,500 years ago, he became, as far as we know, the first person to accurately and scientifically measure the circumference of the Earth. Interestingly, in order to do this, he had to make a couple of assumptions, Kent. First of all, he made the assumption that the sun was a sphere and very far away, so the light coming to us would all be parallel
rays.
Exactly, parallel rays. The other thing he assumed was that the Earth was a sphere. It was round, because if the Earth is flat, this wouldn't work. If you took two popsicle sticks and you stuck them in the ground in your yard, you would get the same shadow length every day, all the time.
Everywhere.
Everywhere. Because if the Earth is flat, everybody's going to get the sun at the same exact angle, and so the length of the shadow, and we know, we've all watched shadows from buildings, flagpoles, people, how in the late evening or early morning they stretch out very magnificently, but at noontime they're as short as they get for local time. And Eratosthenes said, well, gee, if we have two sticks at different points, one north and south from each other at a known distance, and we see the difference in the length of the shadow, or the solar angle, if you want to put it that way, we can measure the difference between them, and we can use this to measure the Earth. And we're going to
Simple math.
Simple math.
Right.
What? Oh, yes.
Not 2 + 2 simple, but not hard.
Not hard.
Not crazy.
Protractor, ruler, and you can do the rest with pencil and paper.
Right.
It literally is 6th grade math.
I think this is a great project for everybody. If you have a flat Earth friend, you need to recruit them to participate in this project to see the gymnastics they'll go through.
Yes, I'm also hoping, if you have children in your life, that you'll reach out to their teacher and have them participate. Now, if you'd like to see videos just on this, you can go to YouTube and look at the Astronomy for Educators channel. Look that up, and there's a couple of videos there, and we'll be putting more up as we get closer. But let's detail all you need.
Now, you're wanting to do this. I mean, this started out just a couple of projects, and it's growing pretty quickly, right?
This has been in my Astronomy for Educators book, which I wrote in 2015, and it got picked up and published by the University of Arkansas in 2018, won the Global Campus Award for Best STEM Text that year. And Professor Sederberg saw this book, and he went through it, and he and I have been colleagues for a while, and he saw this and he said, Daniel, I'm taking a group of physics students and physics teachers to South America in March. Why don't you and I do this project? And I said, okay, but I've got some friends.
It was a eureka moment.
Almost. It was. Yeah. It was. And so I said, you know what? We've got a global audience with How Do You Know? I'm going to be on the Global Star Party tomorrow evening. that's also hosted by Explorer, and we have a global audience there. And I have an awful lot of teacher contacts and colleagues, and so we're going to see how many people we can get to do this.
More data points,
More data points.
more accuracy.
All you need, my friends, is a dowel rod. This is something I picked up at the local home improvement store, and you can do this two ways, Kent. If you do it the simplest way, you actually need two folks. And for the simplest way, I'm hoping we can see this. This is a little circular bubble level, and you can purchase these on Amazon and other sites. And
it has sticky back
this
on
has
it.
sticky back on it. And I'm creating our device live here, friends. We just go ahead, and there we go. We've put a bubble level on to a stick. So now if you're working with a friend, like Kent and I here,
See, I'm going to hold it, right?
good.
So let me, I'm going to put it on my foot,
yeah,
get a little bit height there. Okay, so
your friend would hold it and look down and say, it's level now.
let's do this.
There you go.
Back up a little bit.
Yeah.
We got to stay in focus.
So Kent would be my measuring pal, and he would hold the stick up, and he's got it with the
There we
bubble
go.
centered right now. And what I would have done beforehand is we would have chalked out on the sidewalk or parking lot, Kent, we would have chalked a line that's exactly north-south.
So how do we do that with get it exactly north-south? That's
There's-
not easy to do, but it's easy to do if you know how to do it.
There's two ways. You can get a magnetic compass, and you can look up what's called magnetic deviation. How far off are you in your location? Here in the Springdale area where Explorer Scientific is located, we're off by about 3 degrees.
So by off, he means magnetic north and true north
Are not-
not the same
not
thing.
the same.
And if you pull out your smartphone and use your compass on your smartphone,
It's a magnetic compass.
it's a magnetic
almost always.
compass, but you can, on the smartphone I use, you can go into the Compass app and tell it to use check true north, and it negates out the magnetic
right.
deviation, and now
That's
your
right.
smartphone is going to give you exact reading
Correct.
of true north.
The nice thing, too, Kent, that if your line is within 5 degrees either way, you're going to get a pretty reasonable
So are
answer.
you saying close enough is good enough? Be precise, but close enough is
It's
good
good
enough.
Yes.
Right. Okay. All right.
So the other nice thing
So what
that,
are we going to do? So we've got this stick,
Right.
and we've got a shadow that
And-
runs down that line.
and of course, as the sun moves across the sky, the shadow goes clockwise across the ground.
Mm-hmm.
We're going to set up just before the shadow hits that line, and when it hits that line, we're going to be measuring. The other nice thing I'll tell you, Kent, is a lot of buildings, like school buildings
Mm-hmm.
and public buildings, are set up and built, lined up exactly north-south.
But do we need to know the height of those buildings if
We do
we're
not.
going to use those?
No.
Okay.
But if you've got a building and you check with your compass and you go, you know what? This front of this building runs north-south, or this street runs north-south, you can pretty much put a line down the middle of the sidewalk and you'll be within a half a degree either way.
And so then what are we going to do? So we have this known
Have this-
straight line.
Have this straight line. When the shadow exactly crosses that line, that's local noon because the sun is now at the meridian, and we're going to measure the line from the base of the stick to the tip of the shadow. We're going to measure it and write it down. All we need to record is our GPS location, right? Our latitude and longitude, the height of our stick, and the length of our shadow with the 4 pieces of information, right?
So you're going to measure from the top lip of
top
here to
the bottom.
To the bottom.
Right? And this is a 36-inch dowel rod, and it's got about a quarter inch thick.
Right.
But we'll measure that. We would measure that as accurately as we could, and we would measure the shadow as accurately as we could. And with our GPS data, you can send that back to us. And
Because you're going to have an online form to
we're
put
going to
it in,
have an
right?
online form. You can also email it to me at astronomyforeducators@gmail.com, my regular email address. And we'll take all this stuff, and it's going to be a fair amount of computer processing, friends. Because if we get 100 people, we're going to take the first person and compare it to number 2 and number 3 and number 4 all the way out to 100. So if we get thousands of people, it's going to be a fairly big computer task.
But you could be Eratosthenes. Did I say that right?
Eratosthenes?
Eratosthenes?
Yes.
He's a rascal. It's a hard name to say.
It's a jaw cracker.
If we could be him, just like he had 2 people do it
Right.
in Alexandria and was 1,000.
Syene,
1,000 kilometers
which is
south.
now Aswan, I believe.
Yeah,
in
that's right.
Egypt.
Aswan, you're right.
It's now-
So then it was 1,000 kilometers south,
Pretty much, yeah.
and so they were able to record it, the exact times,
Right.
and then he did the math with 2 data points.
He had the measurements done on the summer solstice because in Syene
There was a well.
there was a well, and it's on the equator, and so the sun shone down the well, no shadow,
Only 1 day a year.
one day a year, summer solstice, and so he had both people measure on the same day. Now he did this because he needs to make sure they were measuring on the same day, but we have calendars.
Right.
And he knew the distance because by the time he got there, the Egyptians had been doing commerce up and down the Nile
exactly
for thousands of
how
years.
long it was.
They knew exactly.
Right.
He was able to look at a map and say, how far south is Syene from Alexandria? And he was able to go to the Library of Alexandria and get, he was the...
He was a librarian, wasn't
he was the librarian there for a
Yes.
while. So he had access to all the up-to-date maps and was able to get a distance. We can do it, friends, with
fantastic.
GPS.
So what I'm saying is, if you have a friend who lives, like we're in Northwest Arkansas.
Correct.
If we have a friend that lives in North Dakota or South Florida,
Right.
we can do the same thing Eratosthenes did
Yes,
with 2 data points.
yes.
And still should be able to come within, what was he, 2.5%?
2.5%,
2.5%. In how many years BC?
about 250, 275 BC.
BC.
Yeah.
He was able to get within 2.5%
Yep.
of the current value of the diameter of the Earth.
Correct.
Using 2 data points.
Yes,
1 hole in the ground and 1 stick.
yes.
And he was able to do the math
Yes.
and figure it. They don't even have to be the same depth. It just has to be,
Right.
you have to
You
know that
don't have to
relationship.
have the same length of rod. I'm assuming that a lot of our viewers in Europe, the Philippines, across
meter
Asia,
rods.
they're going to get meter-long valves.
Diameter doesn't matter.
Diameter
however,
does not.
You want to have one big enough to where you can see that shadow really well.
Yeah,
Yeah.
this is a 3/4 inch, or for our European friends, about 20 millimeters. And this is fine, and it doesn't matter what it's made of. You could use a piece of rebar, you could use a stick, you could use anything you like.
Does height give us more advantage
No.
for accuracy?
No.
Yeah, so a stick this long would probably
That'd be...
push it maybe.
I think something in about a
In the
meter
meter is
will
gonna
give
be-
us great results.
Right.
And the interesting thing is, if we look at the shadow, as the shadow stretches out, it gets blurrier
Right.
because of the angular diameter of the sun. So a really tall, like a flagpole,
Yeah.
you're
At the
going to
end
have
of
a
it's-
pretty fuzzy
Decision.
end of the shadow.
You're going to build in error.
You are.
By having a taller
You are.
stick, and it's not better to be taller because of that whole point right there.
You could do something with a 30 centimeter, 1 foot ruler and get an excellent result. It would be just fine.
So you said there's one way. This is one way. We spent
Yes.
a lot of time talking about one way.
And this requires 2 people.
Correct.
One to hold the rod steady, the other person to make the measurement.
And we're not holding it in the air steady.
No.
We're setting it on
We're
the end
setting
of
it
that
on
line.
the ground. Thank
right?
you. Yes,
setting
we
it
are.
on the end of that line.
We're setting it on the end of that
of
line.
the north-south line.
Now, what if you're by yourself? Mm-hmm. And I sat down and I developed a nice way where anyone can do this by themselves. Takes a little bit more equipment. You have to have, and I'm just going to hold this up for a minute, you have to have a regular camera tripod, friends. And this one, you need a camera tripod that adjusts where the column will get longer and shorter.
I love pushing that down and making the handle spin.
Yes. And what we're going to do now, Kent, we've taken the tripod head,
I see what you've
and I've
done.
just got a 1/4 nut here.
So
And-
this is the removable piece where normally
Correct.
you would screw your camera.
You would screw your camera or your
onto
spotting
it.
scope or your binoculars, right?
right.
And what I've done is I've taken a regular steel ruler. This is a 12-inch / 30 centimeter ruler. And I've taken a nut and I've just bolted it on here.
And it's in the United States it's 1/4 to 20, and in Europe it's like
I
don't remember. It's something
Is it an
16. It's in
M16.
Yeah.
Anyway, folks,
Yeah.
if you've got a tripod, you know what your thread is. You know what your thread is. And so all I've done is bolt this. And the reason I did this is when this is clamped to the top of the tripod, this lets you,
You want me to hold it for you?
lets you hang your stick far enough away from the tripod, And you notice I've taken my stick here and I've put in a little eye screw. You can use a cup hook, like one of those cups you use to hang a coffee cup. And what we do is we just suspend this.
Just like that.
And what I did is I raised the tripod up until this was essentially a pendulum.
And so you just want to get just above the ground.
Well, when it stops swinging, I lower it
Throw it
until
down,
it
okay.
touches the ground,
Yes, okay. 'Cause you,
right?
yeah, and so you don't want to get this low.
No,
it's not
because
gonna-
then it'll wobble.
right, but you want it.
You
Just,
want to lower it
just-
down. You want it still. You want it hanging vertically, because when it hangs, it's a pendulum bob, right? It's a plumb bob. Exactly. So it hangs down, and then you lower it down to where it touches your north-south line, and then you just watch. And I did this weekend at my house.
Yeah.
We've got an old concrete slab out in one of our fields. It used to be part of a house that's not there anymore.
Right.
But it's flat, it's level, and it's aligned north-south.
Yes.
Or within about 2 degrees. Anyway, we went ahead and we put up the north-south line, and we set this up with the tripod, and we hung it, and we measured it, and I was able to get the solar angle to within 0.7% of the actual value.
0.7%.
7/10 of the actual value. According to, I looked it up on Stellarium.
I was going to ask you how you figured
I looked
that
it up
out.
on Stellarium, and I put in my exact GPS location, and I just took, and I went until the sun was at exactly on the meridian, and I said, what's my altitude? That's my solar angle.
Right.
And it came out 37.58, and I got 37.45 with
So-
the shadow.
So
So
when you say altitude, you're not talking
altitude off the horizon.
correct. You're not talking about above sea level.
No.
Right. You're not
No.
talking. That is irrelevant to this
That's
measurement.
irrelevant, right?
It's
Your
irrelevant.
elevation doesn't matter. And I went and tested it actually within about 10 minutes either way, because if you think about the sun traveling in an arc, when it's at the meridian, it's as high as it's going to go. It's traveling almost horizontally.
Right.
So if your north-south line is within 4 or 5 degrees either way, which anybody can get with a compass, easy.
right.
The shadow changes is only a couple of millimeters.
Right.
So it's a very forgiving experiment, Kent. It's easy for everyone to do. 3rd grade children could do this. 8-year-olds could do this easily.
60-year-olds do it.
Well, maybe.
Uh,
I taught 16-year-olds for a long time.
I said 60.
Oh, 60.
60-year-olds.
Oh, sure.
Almost. Yeah.
Sure.
Yeah. As long as they're capable of reading millimeters, and we
Right.
should probably do this. You want this in millimeters, correct?
I do, but if you send me a value in inches, I'll convert for you.
Right.
For
But
all our American friends.
having worked in a welding shop, where
Millimeters is
you had to measure, a 39-foot 6.5 and
Right,
0.6
right.
inches, it was a lot easier just to say this many millimeters.
Right. If you got it to the millimeter, it's great.
Yeah.
If you get it in inches,
You can
I'll fix it for you.
Write an Excel and convert it.
Yeah.
Easy enough.
Yeah, that's
Yeah.
easy enough.
Yeah.
So
This
we
is
can
gonna
put
be
that
fun.
in.
So, what are the dates?
The dates are March 12th to 18th.
Okay, coming up.
That's when
Month and a half.
my colleague, Dr. Sederberg, is going to be in South America with physics students and physics teachers. And he's running a workshop down there. And he said, I want to do this. And I said, we need to go big.
Yeah.
So I would like our entire How Do You Know audience to participate in this if you can. Go ahead and go to YouTube. Take a look at the Astronomy for Educators channel. And when you do that, you'll see a couple of videos right up there right now, Kent. One shows you how to make that device with the tripod. And the second video shows, I did a video of myself using that this weekend and measuring the shadow. And you'll get to see exactly how it's done. It's so simple. And like I said, it's a very forgiving experiment. And even if you're off a little bit, you're not going to ruin things. But we need your date, right? We need your date. We know your time. The reason we do when it crosses the north-south, everybody's measuring it
noon.
local solar noon.
Right.
Right?
It doesn't matter.
So
what
it doesn't
time
matter what
Yeah.
time zone you're in or where you're located. And your GPS is going to give us that information, latitude, longitude, and then the length of your rod, the length of your shadow. Because of the way we set it up where everyone measures the shadow when it's pointing due north, we're all going to get very nice, accurate
So,
data.
to be clear, it's not noon watch time.
No,
It is not the
No.
time on your watch, because the time on your watch, excuse me, is based on the time zone you live in.
Correct.
And your time zone is 15 degrees
right.
wide.
It's a big
It's
space.
a lot of big space, and so it's not, when it's noon here in Springdale, Arkansas, it's not noon in Tulsa, Oklahoma,
No,
as far as
No.
the sun cares.
no, not
And
in,
that's what we
not in
care about.
Vladivostok,
Right.
not in London, not in,
Solar
Andalusia,
noon,
Spain. Exactly.
Solar noon
Right.
is solar noon.
So when your shadow crosses that north-south line, friends, you are at local solar noon, what we all used to call noon years ago before we had
Trains.
GPS trains. Yeah, that's another big story, but yeah. Anyway, so I'm really hoping you'll take a look the Astronomy for Educators channel on YouTube. Take a look at those 2 videos on how to do this, and you'll get yourself a dowel rod and a level. Or if you've got a ruler and a tripod, you want to do this yourself, it'll work out just fine. And those videos will show you exactly how to do it sometime between March 12th and 18th. The reason why we have that big a window, we want to make sure everybody has clear skies. You need a nice
That
sunny
would be
day.
a problem, wouldn't
That would
it?
be a problem. If it's a cloudy day, you cannot get data. And if you extend a little bit beyond that, go ahead, put your date in and say, oh, well, we had clouds from the 12th to the 18th, but the 20th was clear. So here's our data. If we know the date, we can correct for everything.
Does
And,
that create data errors? Start
it
building
does,
up if you get
because
too wide of
if
a,
we think about it as we move through winter and into spring, the sun reaches a higher
Mm-hmm.
altitude each day. Most of us notice that the days are longer, but
Right.
the sun also reaches a higher altitude in our
which
sky,
gives us your shorter shadow.
shorter shadows,
Right.
higher solar angle. But if we know your date, your location, the length of your rod and the length of your shadow, even if you're a little outside our window of March 12th to 18th, you're going to be contributing to valuable data. We're going to prove once and for all the Earth is round, the sun is round, the sun is far away,
Recruit your flat Earth friends to come help.
and we're going to actually be measuring the Earth. Our goal, my friend, is to beat old Eratosthenes and get an answer that's more accurate than 2.5% to the modern.
Oh, there's one thought. I just thought of this.
Yes.
When you turn in your GPS location, that minus sign and the north or south are vitally important.
Yes.
I mean, because if you leave that out, we don't know where you are, because if you don't have the minus sign, that means you're in Eastern Europe somewhere.
You're a half a
right?
world away.
You're literally half a world away from where you
Right.
are right now. And so
Right.
it's important to include, if you have a minus sign or a north-south,
Include that.
Include that. It's vital.
And we're going to go ahead and group these data as tightly, and we'll probably not do time zones. We'll probably do half time zones if we have enough data. We're going to group them by longitude, and the difference in latitude is how we calculate the size of the Earth.
I mean, that's what we're doing, is the difference
Yes.
in latitude.
Yes.
That's what we're measuring.
That's
is
the crucial
latitude.
point. It is not, friends, the distance between cities. There are websites where you can go and find the distance between Tulsa and London, England, any 2 cities you name, and it will tell you the crow flight distance or the great circle distance. But that's not what we want. We want the north-south distance. That's the crucial measurement. How far north or south are you from the other people in the database?
So can you talk about the math real quick, how the math works in a nutshell? Is
Yes.
it too complicated?
No. The math is essentially trigonometry, and what we're going to do is we're going to take your solar angle and we're going to convert it to radians, because when it's in radians, the distance between 2 points is simply the radius of the Earth times the difference in the angle in radians, and that gives us our distance in kilometers. It's really, it's spherical trigonometry, but it's not as awful as it sounds. The calculation is actually multiplying two numbers. You just convert your angle into the right units, and then it's just multiplied times the radius of the Earth, and you're there.
And this is not modern math either.
No.
A guy did it 300 years BC.
Yes.
300, whatever it was
Yes.
BC.
Yes.
He did it well over
Yes.
2,000
And it was known.
years ago.
It was known before him.
Right.
Yes.
Right.
Absolutely.
So,
all right.
All right. Moving on. So,
Let's go ahead and go to today's episode 69 of the How Do You Know program. Today, this has made news, and I've seen this rumbling across the internet, and we're talking about the first observation of population 3 stars. And Kent, you and I have been
pop
talking.
3 stars.
Pop 3
Is
stars.
that a Korean pop
No, it is
group?
not. Population 3 stars, sometimes referred to casually as pop 3 stars. There are 3 generations of stars. Walter Baade was the German astronomer, was the first one in about 1945. And he said, oh, there's 2 populations of stars. There's Pop 1, which is the modern stars, and there's an earlier population of stars, which Baade called Population 2. And he said the difference between them, Kent, is that the gas from which stars are made has been evolving over time.
Right.
When the Big Bang happened and the universe cooled and the first atoms formed, we had hydrogen. Everything would have initially been hydrogen. Electron, proton, hello, hydrogen. And it was still hot enough to be fusion hot in the early universe. So some hydrogens fused to make helium, and occasionally a helium and a hydrogen would fuse again to make a lithium. The primordial percentage, and this takes a lot more math than I have, but we'll rely on the astrophysics community. The primordial percentage would have been approximately 74% hydrogen, 24% helium, and about 2% lithium.
So lithium seems counterintuitive. You'd think it would be oxygen or some other lower element.
We're really talking about element number 1, number 2, and number 3.
Right.
2 hydrogens fused to make a helium, a hydrogen and a helium fused to make element number 3, 3 protons, and that's lithium.
Right.
To build the other elements, which happens over time, stars have to fuse them. Stars have to create them in
Push
their core.
them together.
Correct.
Right?
And-
Crush, heat.
Right.
Right.
Heat and pressure, what physicists refer to as temperature and containment. You've got to heat them up hot enough so when they slam together, they can merge and fuse, and you've got to keep them forced close together. Otherwise, even if they're very hot, the number of times they actually collide will be very small, and fusion isn't efficient. And that's why fusion is so hard on Earth. We can make things really hot, but to make things hot and keep them contained in a single space, that's why a fusion reactor is hard.
And the heat comes when those things fuse together.
They release a lot of
They have to
heat.
release electrons and
They release a lot
Right.
of energy.
and that's because the release
Right. They
to make
release-
it match to meet the structure. Some things have to leave.
Right.
And
They
that
release
produces heat.
They release particles, they release neutrinos, they release gamma rays, and all of those things eventually devolve into heat. And so compression also gives you heat. And so
That's how a diesel engine works.
that's right. Baade, his discovery, or his groundbreaking idea, was that over time, the amount of what the astrophysicists refer to as metals, anything beyond lithium. Now, if you were in chemistry class, you probably learned metals are one slice of the periodic table, about 20%, and it's things like gold, silver, iron, platinum, mercury. But for an astrophysicist, anything bigger than lithium counts as a metal,
Why is that?
because they all function the same way in the cloud as a star is forming. These larger atoms, what we're calling metals for today, they all basically help the newborn or forming star release heat. That's important because it's a gas. And when you heat gases, they expand. If you can release some heat, the compression can be greater, the containment is greater, and fusion is much easier to start. And it wasn't realized until about 1984 that there would have been a population 3 star. I know, they're the first ones. It should have been population 1, but that's
Well, the first ones we figured out were the first ones, and so therefore
that's
they're
the ones
one.
that are around now. The star, our sun, is a population 2 star.
Right. Which means
It's
That-
old.
those original stars did their thing and then went supernova.
Boom, right.
And that scattered their detritus, remains, all the things they had made
Yes.
by fusing more and more things into higher and higher metals
Yes.
in our version of
Yes.
astrophysicist metals until they went bang
Correct.
and scattered themselves out into the universe.
And
Then they started coming back together.
the basic thing about stars, and I'm sure you know this, most of our viewers probably know this, but some may not. The bigger a star is, the hotter it burns. The hotter it burns, the quicker it runs through its
Faster it
fuel.
goes.
And the big hot stars die young and violently.
Those bright blue stars.
The bright blue stars. The bigger a star is, the faster it burns and the younger it dies. The smallest stars, red dwarfs, are projected to have lifetimes on the order of 1 trillion years, 1,000 billion. The universe is 13 to 14 billion years old now. These things are babies. They're going to outlast everything. But yellow dwarfs, like our sun, last about 10 billion years. Bigger stars, like blue giants, last from 10 to 100 million years. Now, how big are we talking about for a blue star? We're talking something on the order of 75 to 150 solar masses. The biggest star we know of is about 200 solar masses, and we only know of literally 4 or 5 of those. They're extraordinarily rare because they're very violent, they're very unstable, and they're likely to go, you know, it's like a piece of dynamite in the furnace. Anything's going to make them go boom.
Yeah. Poke it really good, it might go
Yeah,
off.
bang, contact explosive. So these things, these really big stars, die very, very quickly, on the order less than 1% of 0.1% of the lifetime of our sun. And 10 million years is nothing compared to the trillion-year lifetime of a red dwarf. Well, when the universe was young, there would have been only a tiny amount of lithium and nothing else, no metals. So these stars would have had no metals to help them release
Now,
heat.
these are population 3 stars.
Population 3 stars.
The original.
The original stars.
Right.
So they wouldn't have had metals to help them cool, to help them form small compact stars like our sun, or even like Betelgeuse or Rigel. They couldn't form little teeny tiny blue giants. No, these things, can't we think these things would have been far larger than our solar system?
Oh, yeah.
They would have been, say, 10,000, 100,000 times larger than the diameter of our sun. And people quibble and have different mathematical models about how exactly, why were they this big? Because in order to get fusion started, because you didn't have those helpful metals to release some heat, to help you cool off, to help you compress, we only need to be hot in the core. These original stars were resistant to compression. So their cores weren't hardly any hotter than the rest of them. You just had to have something so gigantic, the entire interior would have been fusion temperature.
And so they started fusing
Absolutely.
hydrogen, helium, lithium, and then into the on down the line, because I can't remember they fuse into up to iron, right?
Up to iron. Number 26
iron.
is as high as you
Right.
can go.
So what's the process? Because I don't remember. Hydrogen, helium into lithium,
Right.
and then lithium and
Lithium into
helium and
carbon,
Okay.
and then you have something called the carbon cycle, and where you build heavier elements up to carbon, of course, friends, is number 6. Oxygen is 8, and nitrogen is number 7. And as you get carbon, oxygen, nitrogen, those are relatively easy to fuse into some of the larger atoms. But here's the deal. Essentially, if you think about it, stars are very efficient recyclers. You start out with a ball of hydrogen, mostly. It makes helium. Well, hydrogen fuses at about 10 million Celsius. Helium requires 10 times higher temperature, 100 million degrees.
Warmish.
Yeah. So when the hydrogen is all gone, helium doesn't automatically start fusing. Essentially, the star goes out, and then the whole thing collapses. As it collapses, it generates more
Because it's
heat.
getting cold.
Correct. Well, there's no fuel to keep the envelope of gases inflated.
Okay. Right.
When these collapse, the core temperature spikes, and boom, you light up the helium fusion process. And so, essentially, these stars' fusion engines burn everything else, and then they collapse and they start burning what's essentially the exhaust, the byproduct.
The ashes of...
They burn the next level of ash, and they reburn and they reburn and they reburn. But each time, Kent, you get less energy out. That's why red giants are red giants. They're burning helium, and they're burning very hot, so they expand.
Right.
They get very large, but they don't last as long, and the surfaces, because they're inflated so large, are cooler. That's why they're redder. And these red stars are burning helium, and after the helium burns, you've seen carbon stars, haven't you? The deep
Yes,
red,
those
orange.
red, like they're like look like Mars almost.
Yes.
Except they're
Yes.
a tiny point
Tiny
of light,
point of light.
not a disk of light.
Right.
Yes.
And they're kind of a Margious orange. Those
Hard to see sometimes.
They are. They're relatively small.
You have to
and
have
quite
dark
rare.
skies. You have to have dark skies
Dark
to
skies
see
and a nice telescope.
them. And a decent telescope.
They are quite rare, but they're beautiful. These are burning carbon. You go up, and each time you switch to a new fuel, you get less energy out. The core has to be hotter, and the life cycle is shorter by about an order of magnitude. By the time you get ready to produce iron, that cycle lasts maybe 1,000 years.
Yeah.
And so
Quick. Very
it's quick.
So one thing is, talk about helium. The Earth doesn't make helium.
No.
The helium that we have in our balloons,
Well,
Is
it's a radioactive product.
it's a radioactive
Right.
product.
It comes from the decay of uranium.
Okay.
But do we fuse and make helium in the core of Earth? No. But do we have uranium primordial from the formation of the Earth that's deep in the Earth, that's decaying, and one of the decay products is helium? Yes, we
Yes.
do.
But that helium,
It's a limited...
originally- it's a limited supply because a limited supply of uranium.
Yes.
But all that original helium and those atoms came from, like everything else,
Primordial.
primordial stars
Yes.
that blew up
Yes.
and gave us the silica in our glasses and the gold in our rings and the lithium in our batteries.
When we use hydrogen, whether you're talking about gaseous hydrogen for hydrogen-powered engines, or you're talking about methane, natural gas, which is a carbon with 4 hydrogens on it, or hydrocarbons, which are fossil fuels, or carbohydrates,
Very
which are
long chains.
which are our carbon-hydrogen foodstuffs. Whenever you talk about that, those hydrogens, the hydrogen in water, hello, the hydrogen in water is all primordial to the universe.
Amazing.
It is.
You know.
And
And some people don't care, and some people, when you talk to them about that, are just blown away when they realize and understand they're connected to the stars.
yes,
Yeah. All right,
So-
so moving on.
these POP3 stars, why are they so hard to find? Well, they were huge, right? They were enormous. Wouldn't they be easy to find? No,
Far, far away.
they're far, far back in time.
Yes.
These were created when the universe was a few 100 million years old. They were all gone by the time the universe was 1 billion years old, 1/13 or 14th of its current age. So when the universe was about 5 to 7% of its current age, these stars were all gone. Now,
Because they burn so fast.
we all know, and we know intellectually, when I look into my telescope or my binoculars, when I look out in space, I look back in time. we see Jupiter the way it was about 3 hours ago. We see Uranus and Neptune the way they were about 6 hours ago. If you can see Pluto, you're seeing something about 12 hours. You're seeing it the way it was 12 hours ago. When we look at the Orion Nebula, which is beautiful in our skies,
1,500 years ago.
3,000.
3,000
About
years ago.
3,000 years. 3,000 light years different. And so when we look at all these things like nebula, and when we look at galaxies, Andromeda is 2.5 million light years away, which means we're seeing it the way it was 2.5 million light years back in time.
And when I do outreach, I use that technique. We'll look at Andromeda, and if you can see it naked eye, I tell people, your body just absorbed energy that has existed unchanged for 2.5 million years. You now have 2.5 million year old energy in your body. And here's the cool thing. From the moment they were born, were created in a star in the Andromeda Galaxy, those photons were destined to fall into your eye right then.
That's right.
If you believe in destiny,
They've been on their way.
They've been on their way to your eyeball for 2.5 million
And if
years.
you're going out tonight to look at Orion, that light was emitted when Pharaoh was first building pyramids in Egypt.
Yeah, it's crazy.
Over 3,000 years.
Astronomy is a time machine, but that still doesn't answer, because the universe is 13 billion years old, but it's been expanding at the speed of light for 13 billion years.
Right.
So it's a really big place.
It is a big place.
And they're very, very dispersed.
And I'm not going to get into the astrophysics of relativity and expansion. We'll set that aside for another show.
We'll set some strictures on the speed limit that we can deal with, sort of, right?
Let's just say, if we're trying to look for these population 3 stars, we need to look back in time to something that's 12.5 to 13 billion light years distant.
At the least.
At the least.
And could be 30.
And of course, the problem with looking that far away...
Dust.
Yes.
Dust.
The universe is a dusty... Nobody has tidied for a long time.
People will they'll buy a telescope, and they'll call and say, there's dust in my telescope, and I need to use that and say, the universe is a dusty place.
Yes, it is. The universe is a very dusty place, and of course, those dust grains absorb light.
Okay, why don't we figure out a way to look past that dust?
We have.
Really?
Yes.
Yes.
And the trick is picking the right wavelength.
Mm-hmm.
Picking the right wavelength. The shorter your wavelength is, and in our visible spectrum from red to blue, those waves are absorbed really well by dust.
Because those dust size are of the same size as the wavelength of white light.
This is exactly why, Kent, when we look at a sunrise or a sunset and the sun is very red, or we look at a moonrise and the moon is very red, very orange, why?
There's a pattern there.
All the other colors of light have been absorbed by the dust in our atmosphere.
Right.
But we notice, the red light comes
through the dust.
And if you go even longer waves into the infrared, it's even better at penetrating dust.
So let's build a telescope that looks in the infrared. How
Exactly. Well, you can't put it on the ground.
Because of the atmosphere.
The atmosphere has water and dust, and water in particular is really good at absorbing infrared or heat. Think about this, friends. You have a pool in your backyard. Even if you have a little, 30 centimeter deep kiddie pool, right? One of those plastic wading pools. You fill that with water coming out of the hose at about 8 or 10 Celsius, or about 50 degrees Fahrenheit, and it's going to take a day or two of sun to warm even that little bit.
But it will warm up.
Eventually, because it's absorbing the heat.
Right.
It's absorbing the infrared. Right. Well, our atmosphere is full of water, full of dust, and they both absorb infrared. So what we did is we built this telescope, and we took it and we put it in outer space. And you know what telescope I'm
James Webb Space Telescope.
That's right, the JWST. The Webb Space Telescope is designed to work in infrared. That's why we put it far away from the Earth at the L2 point. It's about 1 million miles out past the moon. And that's why we loaded it up with liquid helium to chill that thing down and its instruments down to near absolute zero as we could get.
And it's shielded from the sun, so the
It's
instrument's
shielded
in
from the
shade
sun.
all the time.
So it never gets any sunshine, and it's always out there looking. And the Webb telescope has been looking, and the Webb telescope just stunning the number of new discoveries coming from this thing every day.
You know, a show you should do is how the sun shield works, because
That might be
I've,
fun.
I've done some reading up on it, and it's a whole lot more complicated than just
An
put
umbrella.
up some Mylar shields.
No,
right?
it's more
There's
complicated.
a whole. It took them 15, 18 years
And it's 5 layers.
to figure out how to make it shed heat.
Exactly.
And how to fold it up and stuff. It's just fascinating.
Exactly.
That's a great story idea for you, or a show idea.
You know what?
So
we'll do that.
that'll be fun.
We'll do that.
That'll be fun.
I love suggestions, not just from my pal Kent, but y'all.
Oh, you're
can,
the best source for ideas.
Yes.
Yeah.
Our audience is a great source of ideas, and you can put them in the comments. I will see them. Or better yet, drop me a line at Astronomy for Educators, all one word, astronomyforeducators@gmail.com. And the big news is that just recently, people combing through the data, you realize how many terabytes of data the Webb
Has
telescope
already created.
Yes.
In what? 4 months?
Yes.
Something like that? Yeah.
The data is a huge fire hose.
Yes.
We have people today who were doing research on data collected by Voyager
Yes.
half a century
Right.
ago,
Because there's so much.
and
NASA,
Pioneer and Mariner and the
Let-
Viking probes and all of those.
Let alone Apollo.
Exactly.
And the Space Shuttle.
Exactly.
And Hubble Space Telescope.
Exactly.
Right.
And so these people were going through, and they wanted to look through Webb data and find evidence, because these big stars would have a very specific spectra, because there's no metal in them.
Right.
They're all hydrogen.
It would be
and
almost blank. The spectra
Yes.
would have no emission or absorption lines.
Exactly.
Yeah. Oh, they'd have 3
Hydrogen, helium, and you probably couldn't detect lithium from that
because it's
distance.
so small.
So you just look for hydrogen, helium, and it's a very,
Have they found any?
they believe they have.
So no published papers yet.
There are some published papers.
Okay.
But this kind of, what was it Sagan said? Extraordinary claims need extraordinary evidence.
Yes.
So they have put their findings out there. There's a group from Chinese Academy of Sciences. There's a group from the University of Manchester. There's a group from Arizona State, JPL. A number of groups of scientists have said, we think we have evidence. Of course, this is going to be an evolving story for years.
Mm-hmm. Oh, the data we get from the Webb Space Telescope is going to be more revolutionary.
It will be
than what we
transforming
got.
science well beyond our lifetimes.
It'll be more transforming than the Hubble was.
Yes,
Significantly more
yes.
than Hubble was.
Yes.
And it's just going to be fascinating to see what
It
we
will be.
learn, what they tease out of all of
That's
that
right.
data.
And the whole idea that we can look back in time to just after the beginning of the universe and see these first stars that formed that were so different from anything we have today is just such a fascinating story. There's an excellent article in Quantum magazine, and you can look that up on the web. And there are, if you want to go, they also have some links to some of the original papers, which may be or may not be a little deeper than you want to go, friends. But we hope that you'll take a look, and we'll look forward to hearing your comments. It's just about time for us to wrap up. I will not. Thank you. And I hope that you will take a look at 2 of my books. Of course, the most recent one is Star Mentor, available on Amazon, published by Springer, and available in all good bookshops can order it for you. If they don't have it in stock, tell them shame on you and order you a copy. Star Mentor encapsulates almost half a century of my teaching astronomy, written for the average layman who wants to learn how to use their telescope and explore the skies, or the experienced astronomer, somebody like Kent here, who has somebody come up and say, "Oh, please, sir, won't you help me learn astronomy? I have a new telescope."
Why, yes, my wee lad, look through this.
That's right. And it's a lot of people are intimidated when somebody says, "Teach me what you know."
Yeah.
This gives you a guide, step by step, how to take somebody from raw beginner to an experienced amateur. So I hope you'll look that up. And of course, Astronomy for Educators, if you're interested in astronomy as an educational activity, if you have children, if you're a teacher or know a teacher, Astronomy for Educators is now the world's leading online open resource astronomy laboratory manual.
There are fantastic, easy to use, fascinating ways to explain this.
Yes,
It's not,
it's all,
he does it in very simple terms that little kids can understand.
that's right,
Let alone
that's right.
adults understand it too. Very, very simple.
And low cost,
Because his job is to teach teachers how to teach astronomy.
that's right.
And a lot of them have how much background in astronomy?
That would be none.
None.
Yeah.
Not even two. Not diddly and squat. None.
Most of my students want to teach K through 8, and a lot of them are K through 5 elementary school teachers, and people who study and take degrees in math and science, if they're going to teach, Ken, they almost always want to teach high school and college. So almost none of these people, although they'll all be required to teach science, they don't have a background in it. So my job with Astronomy for Educators was to bring it to these young teachers in a way that they can understand, with experiments their children can understand, and with things that cost little to nothing.
That's a key.
Less than $1 per child or $1 per group.
Things you have in your home.
Things you have in your home, like our experiment here with the Eratosthenes gadget. And here we go. What do you need? You need a dowel rod, a little bubble level, and a ruler.
What'd that bubble level cost you?
I got 6 for $5 on Amazon.
Yeah.
And you could probably find something like this. It's a little bubble level, friends. You could probably find it. You know where they would have them? If you don't find it in the home improvement store, somewhere where they have supplies for RVs.
Yes.
Because RVs need to be leveled.
The ones I have on my RV are sort of
And that
like
would work.
sawhorse sort of.
Yeah, that would
things.
work.
Yeah.
But I'm sure you could find them at an RV supply store or
But
camping supply store.
Easiest thing is to use your favorite search engine and search for bubble level.
Yeah,
It was sticky back.
yeah. This is the bubble level with a sticky back. I got a package of 6 for about $5.
Probably easier to do. Although if you have a hot glue gun,
Yeah,
easy enough to buy them without sticky backs.
super glue, hot glue, piece of chewing gum, y'all.
Okay, now we're going to do one with a piece of chewing gum. I think
Okay.
it'll be fun. We have to do that now.
Have to do
Yeah.
it. Arr, arr.
Chew it, stuck it on there, do the experiment, pull it off, keep chewing it.
You are a madman.
Yes, I am.
Well, friends, that's it for this week's How Do You Know program, and we do thank you for joining us. I hope you will join us tomorrow night for the Global Star Party. Look that up on Explore Alliance. I'll be on there, and I'm going to be doing another update for the Eratosthenes project. There are videos I've made just for you that are on the YouTube, on the Astronomy for Educators channel, and they're there for you. You can download them, view them for free. The Astronomy for Educators book is free, and the Star Mentor, when you buy a copy, you support me, you support the How Do You Know program, and you support yourself in growing as a skilled amateur astronomer.
So when you go on that YouTube channel and find Astronomy for Educators, click the like button and ring the bell so you get notified.
Thank you.
Every time he posts a new video.
And in my wild teaching schedule, I don't do that as often as I would like. But certainly be happy to hear from you. Anyway, thank you, Ken.
I'm looking forward to this Eratosthenes product. Did I get
Project,
it right?
there you go.
This is going to be fun, y'all, and you need to participate.
That's
Get
right.
your kids' schools, get your parents at a nursing home to participate.
That's right.
Whatever. If my dad was alive, he would love this.
And Dr. Sederberg is developing a teacher's worksheet, which of course anyone could use. And when he gets finished with that in the next couple of days, I will be posting it up on my Facebook page. I'll also be posting it through the Explore Alliance, so you all can download it. And the video will tell you exactly what to do. It's easy, it's fun. I hope you'll join us. International Measure the Earth Day between March 12th and 18th. And folks, Kent and I both wish you clear skies, and thank you for joining us.